Let's talk about a confidence interval for the mean. First, a confidence interval for the mean when sigma, the standard deviation, is known. If a variable is normally distributed, then there's a 95% chance that its value is within 2 standard deviations of the mean. In other words, there's a 95% chance that its value is going to be between mu minus 2 sigma and mu plus 2 sigma. Here's mu in the middle here. Mu is the population mean, sigma is the population standard deviation. Well, let's look at x bar. X bar is normally distributed. The sample mean x bar is normally distributed if either x is normally distributed or the sample size n is large enough, say n is greater than 30. In either case, if x has mean mu and standard deviation sigma, then x bar is normally distributed with mean mu and standard deviation sigma over square root n. So there's a 95% chance that mu is within 2 standard deviations of x bar, because x bar is normally distributed, just saw that on the previous slide. Really, we mean 1.96 standard deviations. Okay, 95% chance that mu is within 2 standard deviations of x bar. Another way of putting this is that there's a 95% chance that mu is between x bar minus 1.96 sigma over square root n. This is the standard deviation of x bar. And x bar plus 1.96 sigma over square root n. This, again, is the standard deviation of x bar. The probability that mu is going to be between these two values is 0.95. This interval from x bar minus 1.96 sigma over square root n to x bar plus 1.96 sigma over square root n is a 95% confidence interval for mu. There's a 95% chance that the actual value of mu is in this interval. If we take samples and use them to construct confidence intervals over and over again, then 95% of those confidence intervals will contain the population mean mu. That's another way of looking at it. Okay, so again, the interval, this interval is a 95% confidence interval for mu. Another way to put it is that the endpoints of this 95% confidence interval are x bar plus or minus 1.96 sigma over square root n. Here's an example. A study of 66,831 dairy cows found that the mean milk yield was, care to guess how much milk each cow produces on average per milking? It's a whopping 12.5 kilograms. It's almost 30 pounds of milk each time it's milked. Amazing. Assume the standard deviation is 4.3 kilograms per milking. I'm not just making that up. That comes from the data. Construct a 95% confidence interval for the average milk yield in the population. Okay. The endpoints of this 95% confidence interval are x bar plus or minus 1.96 sigma over square root n. So let's plug in the numbers we know. X bar, the mean, population mean, was 12.5. It's not the population mean, it's really the sample mean, sorry. And then sigma, 4.3, and n is 66,831. So when you crunch the numbers, it turns out the interval from 12.467 to 12.533 is a 95% confidence interval for mu. That's a pretty tiny interval. The reason it's so small is that our sample size is so large, almost 67,000 cows. Let's say we want to construct a 90% confidence interval for the average milk yield in the population. Okay, 90% confidence interval is going to be a little bit smaller because we're only 90% confident that it falls into this interval. We're 95% confident that it falls into this interval. So, okay, 90% confidence interval. In general, the endpoints of a two-sided confidence interval for mu would be x bar plus or minus z sub alpha over 2, sigma sub x over square root n. That's where we find z sub alpha over 2 in this chart. Here we've got a 90% confidence interval, so we're looking at 1.645. That'll be our z sub alpha over 2. Okay, we need to talk about what all of this means. Two-sided confidence interval. So you're going to have, it's going to be somewhere between here and here, and then it's not going to include this stuff in the tails. That's what we mean by two-sided. Again, the endpoints of the confidence interval are going to look like this. Z sub alpha over 2, since it's a 90% confidence interval, we're going to have that, 1.645. What do we mean by z sub alpha over 2? What on earth is that? Well, we have a 90% confidence interval. That means another way of putting this is our confidence level is 0.9. So to find a confidence interval for the mean, we need to know what the z value is, okay? So if this middle stuff is 0.9, that means the stuff at either end adds up to 0.1. It's all got to add up to 1. So that is our level of significance. Alpha equals 0.1. That means the area on either side is going to be 0.05. That's alpha over 2. So that's where a z sub alpha over 2 comes from. Z sub 0.05, and z sub 0.05 in this case, again, is 1.645. So that's what we mean by z sub alpha over 2, z sub 0.05. Okay, so we've got our values. Now let's plug them in. So let's construct that 90% confidence interval. The endpoints of the 90% confidence interval will be x bar plus or minus 1.645 sigma sub x over square root n. X bar was 12.5. Again, 1.645. That's what we have for a 90% confidence interval. Sigma is the same as before, n is the same as before. Our 90% confidence interval is 12.473 to 12.527. What do we mean when we say that this is a 90% confidence interval for mu? There is a 90% chance that the actual value of mu is in the interval from 12.473 to 12.527. Now let's talk about the confidence interval for the mean when sigma is not known, which of course is far more likely. Because if you don't know sigma, if you don't know the mean, you're probably not going to know the standard deviation. Okay, construct a 95% confidence interval for the mean number of pets in the households of college students. Suppose that the sample of size 45 students yields x bar equals 2.0 pets, and the standard deviation is 0.7 pet. 7 pets, that's what we've got. None of this 2 pets for us. In months gone by, we've had 1 dog, Lola, 3 cats, 2 chickens, we can keep those in our backyard, and a bearded dragon. We got roped into getting all these animals because our youngest child's an animal lover. Okay, so again, we want our confidence interval 95%, n equals 45, x bar is 2.0, s equals 0.7. The endpoints, we know what those are. X bar equals plus or minus, t sub alpha over 2, s over square root n. See, when we don't know the standard deviation, we use the t distribution instead of the normal distribution. The t distribution is a little bit fatter in the tails, so our value of t is going to be bigger. Our confidence interval will be bigger if we don't know sigma, the standard deviation. Okay, so t sub 0.05 over 2 is t sub 0.025 with n minus 1 equals 44 degrees of freedom. Oh my goodness, what degrees of freedom? Yeah, you have to take into account how many pieces of data you have. In this case, 45 students, that's our n. So the number of degrees of freedom is going to be n minus 1, which is 44. You'll see how that comes into play in the chart in a moment. So we look at the t distribution table. It's in the 4th table in the Appendix D of our textbook. So you go to My Lab Stats, you choose eText, then go to the end of the book, or you could just enter t distribution table into a search engine like Google, and it'll get you there. Okay, so the one in the back of the book looks like this. We want to focus on, let's focus on this. So the column, we've got a two-tail probability is 0.05. Those two add up to 0.05. So this is the column we want, two-tail probability 0.05. 0.05, again, is our significance level, alpha. The row determines the degrees of freedom. In this case, that's n minus 1. That's 44. 44 just goes to 40. There's no 44 in this table. And so we just play it conservative. We round down to the next, which is 40. So we want row 40 and column 0.05, this middle column. So it looks like t sub 0.025 is going to be 2.021. That's what we end up with. So we plug that into the formula. X bar plus or minus t sub alpha over 2s over square root n. X bar 2s, our standard deviation, sample standard deviation 0.7. N is 45, t sub 0.025 is 2.021. Plug everything into this formula, and we find that the 95% confidence interval is 1.79 to 2.21.